This problem is from chapter 22, number 10, and I figured as I'm going to read it, I actually picked up this animation, so I'm just going to play this animation. And you can read through it. It actually doesn't have any voiceover except mine that you hear right now. And I'm just going to read the problem from the book, which more or less goes along with what you're seeing here. So you hear it slightly different than the way you see it. The problem in the book is, in 1909, Robert Millikan was the first to find the charge of an electron in his now famous oil drop experiment. In that experiment, tiny oil drops were sprayed into a uniform electric field between a horizontal pair of oppositely charged plates. The drops were observed with a magnifying eyepiece, and the electric field was adjusted so that the upward force on some negatively charged oil drops was just sufficient to balance the downward force of gravity. And that's kind of what you see here in this animation. From left to right, by the way, you do see X-rays coming out, which is charging the oil drops. Here is a question: why did Millikan select only oil drops for his experiment? And I quite couldn't understand that little diagram they showed there. Why not water? It turns out, I looked it up, it says the oil was of type usually used or was chosen because it had an extremely low vapor pressure. Ordinary oil would evaporate under the heat of the light source, causing the mass of the oil drop to change over the course of the experiment. That's also why water or any other liquid was chosen, because it would just evaporate too quickly under the heat of the light source. They needed to be a light source because this was visually observed, so somebody would sit there with a microscope and actually observe the droplets drifting. So it goes on in the book's problem, that is, when suspended, upward force QE, there's the electric force, just equaled mg, the downward gravitational force. Millikan accurately measured the charges on many oil drops and found the values to be whole number multiples of 1.6 times 10 to the negative 19 coulombs, the charge of the electron. For this he won the Nobel Prize. I believe he was the second US American to win the Nobel Prize in, I want to say 1912, 1920, somewhere around there. Overall, I did the experiment myself when I was in college, and it's a relatively boring experiment and tedious too, because you just have to sit there and you have to watch that oil drop floating and measure as you go along. In any case, let's do the calculations the way they ask us to do them. So, if a drop of mass 1.1 times 10 to the negative 14 kilograms remains stationary in an electric field of 1.68 times 10 to the 5th newtons per coulomb, what is the charge of this drop? So it says problem A, and then they give that, they say, okay, here's an oil droplet, and it has a mass of 1.1 times 10 to the negative 14 kilograms, and as you saw, because of gravity it would fall down. But then there is an electric field E, so because of its own gravity mg it would fall down, but then there is an electric field just of magnitude 1.68 times 10 to the 5th newtons per coulomb, and it is adjusted in such a way that it pulls up the electron with Q times E, charge times the electric field. What is the charge of this drop? So this force over here is the same as this force over here, except one of them is negative and the other one positive, but in magnitude they're the same. So I said mg equals to Q times E, and they're asking for charge, so the charge equals mg divided by E. You can see the algebra. All I did was I took the E from here, put it to the other side, mg divided by E, and that equals Q. That's all I did. Okay, and then I plug in the numbers here. The mass 1.1 10 to the negative 14. The acceleration due to gravity. I'm going to use the 9.8 meters per second squared. Makes it a little bit more accurate than our typical 10 divided by the electric field of 1.68 times 10 to the 5th newtons. That's also because they give us 2 and 3 significant figures here, so I might as well use the acceleration due to gravity with 2 significant figures and plug that in on the calculator. Let's see. There we go. Okay, just a little bit out of the picture. There it is. Almost there. 1.1 e negative 14 times 9.8 divided by 1.68 10 to the 5th. Okay, the way I just wrote this here, 1.68 e5 works without parentheses. If you tried 1.65 times 10 to the, which is this little dash here, 5th power, you would have to put it in parentheses, because otherwise your calculator interprets it as a multiplication rather than a division, which is what it is. It's a division. Okay. Anyway, enter, and I come up with 6.4 times 10 to the negative 19. So 6.4 times 10 to the negative 19, and the units, they look really bad here. Kilograms, meters per second squared, and then times coulombs and divide by newtons, because I multiply with the reciprocal of this one here. So really bad units, but overall these are all standard units, and what should come up with is the standard unit for the charge, which is the coulomb. So I'm just going to write coulomb there. So that's the answer to the first part. Then there is part B that says, how many extra electrons are on this particular oil drop, given the presently known charge of the electron? Well, this one here, so I look up the charge of the electron, and it says 1.6 times 10 to the negative 19, and that kind of looks similar to the charge of the electron. So compare our answer 6.54 times 10 to the negative 19 to the electron charge of 1.6 times 10 to the negative 19 coulombs, and we can see that that number here is 4 times larger as this one, which means that there must be 4 electrons, extra electrons, sitting on the oil drop that are attracted upwards due to the electric field applied in this experiment, and that just is enough force to hold it up against the oil drop's own weight. If there had been fewer electrons, then this force here, this upward force, wouldn't be as large, and the oil drop actually would fall down with 3 or fewer electrons. If there had been more electrons, then this force here would be larger than the weight, and it would actually start drifting up. But the 4 electrons here makes it in such a way that this force here balances this force, just as it is written here.